Unit Operation Classroom. Today we are going to discuss how to find the ultimate period in Ziegler Nichols tuning. Uh, and my name is Shekhar Bhattacharjee. The problem is considered three identical, non-interacting, important, first order important processes in series, each having unit gain and time constant of 2 minutes. Okay, so we look into it. The tuning of proportional controller using closed loop Ziegler Nichols technique is considered. So first read this one from any standard textbook or your college lecture notes, how that is done. So which one of the following is the ultimate period of sustained cycling in minute per cycle? So it is important to know what is this tuning technique and how these are determined and where are the actual applications of these particular Ziegler-Nichols tuning technique, where they are used and why they are used. Let us see an example. Let us assume that it is some pure water or some processed fluid assumed is coming and we have to make it acidic. So we'll be adding concentrated hydrochloric acid system to it, which goes through a control valve here. And so this water or the processed fluid it just goes by gravity from one tank to the other tank. So there is the level in each tank is not dependent on the previous tank. So that's why it's a non-interacting tanks. Three non-interacting tanks in series, each having a time constant of 2 minutes. And as I said, the gain, of course, as we look into it, is a unity gain. This concentration of hydrochloric acid is measured here in this transmitter. So that is sent to the controller, which compares this with the desired set point, and the controller output is sent to this control valve. So here, of course, the process variable is going to be the outlet concentration of hydrochloric acid, and the manipulated variable is going to be the concentrated hydrochloric acid flow rate. Okay. Now let us translate this one into a block diagram. So as you can see, this is my set point here. This is a very standard negative feedback control loop. So that is my proportional controller, and these are the three unity gain the first order systems. So that's why these are one unity gain, and these are first order systems having a time constant of 2 seconds. Okay. So this is my controlled output, and this, of course, is assuming unity feedback. The transfer function here, RS is the set point, and this is the controlled output. A very standard. So as we see, there are three identical first order systems in series, each with a gain of 1 and time constant of 2 minutes. So the transfer function of the overall process for each one, this is 1 over 2s plus 1. So for the three process, it's going to be this one right here. So for a proportional controller with gain Kc, this open loop transfer function is going to be this. This is very standard. So we know that. Okay, so for the closed loop transfer characteristic equation is going to be this. We know that, and we substitute here. That's what we get. So at sustained oscillation, the closed loop poles lie on the imaginary axis. So as you change the value of Kc, we need to find out where the sustained oscillation starts. Based on that, we'll be doing the controller tuning. For sustained oscillation, the ultimate gain, we substitute as G equal to this one. This is very standard, and the phase lag, of course, is negative 180 degrees. We know that. This is the magnitude condition, and of course, the loop phase lag is going to be 180 degrees or pi radians. So this is very standard, and from there to omega is to 10 pi over 3. That's root over 3. So this is equal to, that's the ultimate frequency. Okay, so when there's a sustained oscillation using that system for that particular process. Once we know that, then the ultimate period, of course, is given by this one right here. So the ultimate period is 4 pi root over 3 minute per cycle. So C is, of course, the correct option here. This is a very standard. I'm not going into the details. So this is the standard period, ultimate period during a sustained cycling, which was found by the Ziegler Ziegler Nichols technique. So let's see what the additional information to calculate the ultimate gain. Don't need to do that for this particular problem, but let's see if we want to find that. We know the closed loop transfer function is this one. We have seen it. So we substitute S equal G. We get U, and so this is what we get. This one right here. So this one right here. So taking magnitude on the both sides, of course, is going to be this and magnitude on the both sides of this one. We get this one right here. And we know the magnitude of complex number is given by this. Again, very standard. So if we apply that, we get this value and we get this k is equal to 8. So the ultimate period is going to be this one right here, and ultimate gain is going to be this one right here. So this is the answer that is required. So option C is the correct answer. So if Ziegler-Nichols tuning is applied, so then we can find out the settings for if it's a proportional controller, PI controller, and PID controller. These are, of course, the starting values, and the actual plant, of course, needs careful tuning. Practical application of this problem, temperature control in a series of heat exchangers. So assuming those to be the first order process, a process stream is being heated from ambient temperature to reaction temperature in three shell and tube heat exchangers in series. Each exchanger acts as a first order system with its own thermal capacitors, that is time constant. So significant time lag between uh, changing steam valve opening, that is the steam flow rate, and the temperature change at the final outlet. So significant lag happens if there are three heat exchangers in series. Okay, by the time you change the flow rate, of course, the final temperature, there's a significant lag. So that's where what you do when several heat exchangers are connected in series, the total lag becomes significant. And if the controller gain is too high, if you set it's too high, then of course the final output temperature will oscillate. Okay, which we don't want. So Ziegler-Nichols loop method is used by control engineers to find the KU and PU. These values are used for tuning the PID controllers. Composition control in a train of CSTs. In pharmaceutical industry, CSTs in series are often used to achieve high conversion and selectivity. Waste heat neutralization tanks also in a multi-stage mixing tank. If the control valve is cycled too fast, that is mimicking the PU, acid caustic flow will overshoot, causing the pH swing between the acidic alkaline to highly alkaline acidic. So, if you just keep the value of Kc very high, there's a very high dose here, and of course, this final pH will keep on oscillating. So, this Ziegler-Nichols controller tuning is widely used for controller settings. Uh, so Ziegler-Nichols loop method is used to control by control engineers to find Ku and P. These values are used for tuning PID controllers. These are, of course, again known, and this, of course, is the answer we wanted, and that option C. So that is very easy, which we have seen right here. That's a very easy, and so this option C is the correct option.